Hello everyone. So in today's session we have to solve some question. The first question is the correct set of quantum number for the last electron of sodium plus. Correct set of quantum number. Quantum number for last electron of sodium. Okay, so we have to know about the last electron quantum number of sodium plus. So there are basically four quantum number. First is principal quantum number, other is azimuthal quantum number, third is magnetic quantum number, and last one, that is spin quantum number. Okay, so principal quantum number tell us about the number of shell as well as size of that element. Azimuthal quantum number that tell us about the shape of the orbital, whether the orbital will be spherical or dumbbell or double dumbbell, whatever it is. Magnetic quantum number tell us about the spatial arrangement in 3D. Okay, how the orbitals subshells will be located on the axes. That tell us our magnetic quantum number. And spin quantum number tell us about the spin of an electron in a particular subshell. Okay, whether it is plus half or minus half. Okay, which is denoted by this and this sign. This is plus half, this is minus half. Okay, now this is some basic thing about the quantum number. Now we have to know about all the four quantum numbers of sodium plus. Okay, so for that we have to write down the electronic configuration of sodium. Okay, so we know that atomic number of sodium is 11. Okay, so electronic configuration will be 1s2, 2s2, 2p6 and 3s1. In case of sodium plus, this one electron of 3s will be removed. Then the electronic configuration will be 1s2, 2s2, 2p6 and 2p6. That will be enough. Okay, so we have to know that for n equal to 2, in this case we have to know about 1, 2, 3, 4, 5, 6. In this case we have to know all the four quantum number for this particular electron, and for this electron the value of n, that is principal quantum number, that is 2. Okay, this is our principal quantum number. Okay, for any given n, the value of L will be, that is azimuthal quantum number, that is from 0 to n minus 1. So in this case 2 minus 1 means 1. There are two values for this n, 0 and 1, and 0 represent S subshell and 1 represent P subshell. Okay, in this case this is lie in P subshell, so the value of L is 1. Okay, from here we know the value of azimuthal quantum number. We know the value of already principal quantum number. Now we know the value of azimuthal quantum number. For any given L, that is azimuthal quantum number, the value of magnetic quantum number M, that will be from minus L to plus L, and the total value is 2L plus 1. Means in this case, if value of L is 1, so 2 into 1 plus 1, total 3 value will be there. Total 3 value of magnetic quantum number M is possible. So in this case, from minus L to plus L, minus 1, 0, plus 1, minus 1, 0, plus 1. Okay. So this electron lie in this plus 1. Okay. So here the value of M for this particular electron is plus 1. Okay. So we got to know about 3 quantum number. Now we have to finally know about our last quantum number, that is spin quantum number. So as we can see, the last electron is negatively downward spin. So from this, the value of electron spin quantum number will be minus half. According to maximum multiplicity rule, the electron filled in that way so that the multiplicity will be maximum. That is why all 3 electrons, first the orbital try to half fill, then after that the pairing occurred. So in this way, 1, 2, 3, 4, 5, 6, number of 6 electron downward spin, s is equal to minus 2. So all 4 quantum number will be n is equal to 2, value of L is equal to 1, value of magnetic quantum number is plus 1, and spin quantum number is minus half. So from here, this will be your answer. Okay. Now we have to look some other question. Okay. So our next question, here we have some statement. We have to state whether this statement is true or false. Okay. So first statement, which is number of electron having L is equal to 0 is 10 in palladium. Okay. Number of electron for L is equal to 0 is 10 in case of palladium. This is true or false? For this we have to check if L is equal to 0, then in previous question, as I already mentioned, that L is equal to 0 represent S subcell. Okay. Similarly, L is equal to 1 represent P subshell, 2 represent D subshell, and 3 represent F subshell. Okay. In this case, we have to find number of electron, total number of electron that lie in S subcell. Okay. For that, we have to know about the electronic configuration of palladium. In case of palladium, the atomic number of palladium is 46. So first write down the electronic configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2 and 3d8 and 4d8. Okay. So here the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2 and 4d8. That should be electronic configuration, but actually the case is different. This 2 electron of 5s2 jump here from 4d subcell. We know that half filled and full filled atomic orbital is more stable. So for that condition, 2 electron from S subcell jump to 4d subcell, and that stabilize this palladium more. Okay, so what will be degenerated electronic configuration? The degenerated electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 and 4d10. Okay. Here 5s will have no electron. So in the question is asking about the number of electron for L is equal to 0 is 10. Okay. So here S subcell, S subcell, S subcell, S. Total number of subcell 4s subcell, and number of electron will be 2 plus 2 4 plus 2 6 plus 2 8. So for L is equal to 0, that is S subcell, the total number of electron is 8. It is not 10. That is why this statement is wrong. Okay. Total number of electron for L is equal to 0 in case of palladium is 8. It is not 10. That is why this statement is wrong. Okay. Further, we move to our next question, which is the value of Z effective for 3d electron of chromium and palladium. Okay, chromium and 3d electron of manganese is same as number of electron in D subcell of chromium and manganese are same. Okay, so we have to know about the Z effective of chromium and manganese in case of 3d electrons. For that, we have to write down the electronic configuration of chromium and manganese. As we know, the electronic configuration of the atomic number of chromium is 24 and atomic number of manganese is 25. So from here 1s2, 2s2, 2p6, 3s2, 3p6. Okay, 2p6, 3p6 and 4s1 and 3d5. That is the electronic configuration. Okay, one electron of 4s jumped into 3d subcell for stabilize this particular element more, because this 3d subcell is exactly half filled. 1 2 3 4 5. Okay, and in case of manganese, the electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d5. Okay. We have to calculate the Z effective for this electron. Okay. The actual configuration will be 4s2 will be here and 4s1 will be here. Okay. So this 3D subcell lie before 4s subcell. Okay. And we have to calculate the Z effective in 3D subcell. So what is Z effective? There are two types of force which work on a particular electron. Okay, one is force of attraction and other is force of repulsion. Attraction due to opposite charge and repulsion due to same charge. Okay, that is negative because of electron. So in this case, this particular electron feel two kind of force. One is attraction charge due to this nucleus, positively charged nucleus, and other is repulsion because of this electron, this electron, this electron. Okay. So for S and P electron, the electron which lie in S and P subcell, for that a value of for N subcell, if this electron lie in same orbital, so that will produce around 0.35. This is magnitude of repulsion by an electron which lie in same orbital as other electron. Okay. For n-1 orbital, the value of this is screening effect or shielding effect is 0.85. For n-2, n-3 and so on, that will contribute 1. Okay. So for S and P electron, this value will be like this. And for D and F subcell electron, the value, if electron lie in the same cell orbital, they contribute 0.85, and for n-1, n-2 and so on, they contribute 1. Okay. So we know about the value. Okay. So this is some basic thing about shielding effect, or we can say. So what is Z effective? Z effective is nothing but the difference between this magnitude of repulsion because of the same charge of electrons and the atomic number. So Z effective will be